Hey friends, welcome to the YouTube channel All About Electronics. So in the last couple of videos, we learned about the programmable ROM and the PLA. So similarly, in this video, let us learn about the another programmable logic device which is known as the PL. So in the earlier videos, we have seen that in this programmable ROM, we have a fixed AND gate array and the programmable OR gate array. Similarly, we have seen that in case of the PLA, both AND gate and the OR gate array are the programmable. So similarly, if you see the PAL systems or this programmable array logic, then in these systems, the AND gate array is the programmable while the OR gate array is the fixed one. That means in this case, the connections between the OR gate and the AND gates are the fixed one. That means here, the each OR gate will have the fixed number of AND gates. Now if you recall, then in case of the PLA and the PROM, the connections between the AND gate and the OR gate array were the programmable. But in case of these PL systems, these connections are the fixed one. But of course, here the connections between the inputs and the each AND gate array are the programmable. For example, in some PAL system, if we have a 3 inputs A, B and the C, then the each AND gate will have total 6 programmable AND gate connections. And depending on the user requirement, some inputs can be connected with the AND gate. And in this way, it is possible to generate the desired product term for the each AND gate. So if you see the typical PAL logic IC, then it consists of multiple such OR gates. And in the each OR gate, the fixed number of AND gates are connected. So like I said earlier, the connections between the inputs and the each AND gate are the programmable. So here, the output of the each OR gate will be in the sum of product form, and therefore here the each OR gate output may represent the individual functions. So if the PAL system has total 3 OR gates, then it means that it can implement the 3 different Boolean functions. So as you can see, in this particular PAL system, the each OR gate has the same number of AND gates. That means here if you see, then the each OR gate has total 3 AND gates, and therefore here each OR gate can generate 3 product terms. But in some PAL ICs, it is quite possible that the different OR gates may have the different number of AND gates. For example, in this particular programmable array logic, the one OR gate has the 5 AND gates or the 5 product terms, while the other 2 OR gates has the 3 AND gates. So depending on this PL IC, we may have a different number of AND gates connected with the each OR gate. But irrespective of the number of AND gates, the connection between the AND gate and the OR gate array is the fixed one. Now if you compare the PAL system with the PLA or this programmable logic array, then typically for the same number of inputs, this PL has a less number of AND gates connected with the each OR gate. For example, in the previous video, we have seen the 3 input PLA, and we have seen that has a 5 programmable AND gates with the each OR gate. Now for the same number of inputs, if you see the PL system, then typically it has a 3 to 4 product terms with the each OR gate. That means in this PL system, for the each OR gate, the number of product terms that we can generate is the limited. But sometimes in this PAL system, it is quite possible that we may want to implement the Boolean function which may require at least 5 to 6 product terms. So in that case, it seems like we cannot implement that using this PL systems, right? So to overcome this issue and to implement the Boolean functions with the more product terms, typically in the PAL system, the sum outputs are fed back to the input side and they are used as an input for these other OR gates. For example, let's say we want to implement this logic function using the given PL. So in this PL system, if you see the AND gate array, then by default, the each input and its complement is connected with the AND gate. So here, since the input and its complement are connected with the AND gate, so by default, the output of the each AND gate will be equal to 0. But using the programming, it is possible to remove some of the interconnections, and it is possible to generate the specific product term for the each AND gate. So to implement this output function, as you can see, we require total 5 product terms. So what we can do? We can implement the 3 product terms, that is AB plus BC plus AC using the first OR gate. Because as you can see, the output of the first OR gate is connected back to the input side. That means in the remaining 3 OR gates, if required, then we can use this output as an input for these AND gates. So here, this line represents the F1 output, but the second line represents the F1 dash. So here, in the second OR gate, we can connect this F1 input to the one of the AND gate. That means now, the output of this first AND gate represents the AB plus BC plus AC. And using the other two AND gates, it is possible to generate the other two product terms. That means now, the output of the second OR gate in this PAL system will have total 5 product terms. So in this way, in this programmable array logic, by providing the feedback from the output to the input side, it is possible to implement a Boolean function which may require the more product terms. So now, let us take one example and let us see how to implement some logic circuit using this PL. So let's say this is the truth table of some logic circuit, and as you can see, it has a 3 inputs and the 4 outputs. So now, let us try to implement the same circuit using the PL which was shown earlier. So in this programmable array logic, since the limited number of AND gates are connected with the OR gate, so we have a limited number of product terms with the each OR gate. That means here, the first step is to find the Boolean expression for the each output and try to minimize this Boolean expression. Now during the logic function implementation process, if you compare the PL system with the PLA, then here, unlike the PLA, the output of the AND gate is not shared with the each OR gates. So in case of the PLA, if you recall, then the output of the AND gate was shared with the each OR gate. So if the two outputs have the same product term, then that common product term can be shared between the two outputs. For example, if the AB is the common product term between the two outputs, then the same AND gate output will be shared between the two OR gates. And therefore, there is no need to generate the same product term once again. But if you see the programmable array logic, then that is not the case. So in case of the PL, if this AB is the common product term between the two functions, then here we need to generate it separately for the two outputs. That means in case of the PL, we do not have the luxury of sharing the same product term between the different outputs. Alright, so keeping that thing in the mind, let us come back to the question and let us try to minimize the Boolean expression for the each output. So here, if you see this output F1, then it is equal to 1 for the 4 different minterms. So first of all, let us write these 4 minterms in the K map. So if you see this K map, then here we can combine these two minterms, and likewise we can combine this minterm M4 and the M6. And as you can see, it is not possible to combine this minterm M1. So based on these 3 groups, this is the minimized expression for this output F1. So here I am assuming that you already know about the K map, and you also know that how to minimize the Boolean expression using the K map. So for more information, you can check these videos related to the K map. Alright, so this is the first expression for this output F1. So similarly, this output F2 is equal to 1 for the 5 different minterms. So first, let us represent these 5 minterms in the K map. So here, we can combine this minterm M3 and the M7, and likewise, we can combine the minterm M0 and the M1. And similarly, we can make the group of this minterm M0 and the M4. So by making these 3 groups, it is possible to cover all the minterms. And based on these 3 groups, this is the minimized expression for this output F2. So similarly, if you see the function F3, then once again, it is equal to 1 for the 5 different minterms. So once again, let us represent these 5 minterms in the K map. So here, by making these 4 groups, it is possible to cover all the minterms. And corresponding to these 4 groups, this is the minimized expression for this output F3. So if you closely observe this output F3, then here, the first 3 product terms are same as the function F1. Therefore, this F3 can be written as this F1 plus AB. So later on during the implementation, we will see that why it was written like this. So similarly, now let us see the output F4. So if you see this output F4, then it is equal to 1 for the 5 different minterms. So once again, let us write these 5 minterms in the K map. So here, by making these 2 groups, it is possible to cover all the minterms. And these 2 groups corresponds to C and the A bar B. That means the minimized expression for this output F4 is equal to C plus A bar B. So in this way, we got the minimized expression for the each output. So now, if you observe these 4 expressions, then except the function f3, all the expressions have less than 4 product terms. And they can be easily implemented using the given PL circuit. So here, this function f3 has total 4 product terms. But as we have seen earlier, the first 3 product terms are same as the f1. So here, we can write this function f3 as this f1 plus ab. So we know that in the given PL, in one of the output, we have the provision to use the output as an input. So here, what we will do, we will implement the function f1 using the first output. And after that, we will use that output as an input to implement the function f3. So here, to implement the function f1, we require the 3 product terms. And out of the 3 product terms, the one required product term is equal to AC bar. So here, only A and C bar are connected with the first AND gate. And if you see the remaining connections, then they are removed from the first AND gate. Likewise, the second product term is equal to BC bar. Therefore, in the second AND gate, only B and the C bar input are connected. And likewise, the third required product term is equal to A bar dot B bar dot C. So these 3 interconnections corresponding to A bar, B bar and the C are connected with the third AND gate. That means now, the output of the first OR gate corresponds to the function f1. And likewise, the function f2 and f4 are also implemented. So in the function f4, since only 2 product terms are required, so only 2 AND gates were used. And for the third AND gate, all the interconnections will be kept as it is. So here, instead of showing all the interconnections over here, the cross has been marked on the AND gate itself. That means here, the output of this third AND gate will be equal to 0. And based on the interconnections for the 2 AND gates, this function f4 will be equal to C plus A bar B. And likewise, this function f3 is also implemented in the same way. So to implement this function f3, as you can see, the input f1 which is coming from the first output is connected to the first AND gate. That means the output of this first AND gate is equal to AC bar plus BC bar plus A bar B bar C, or that is equal to f1. Likewise, the second required product term for this function f3 is equal to AB. Therefore, the inputs A and B are connected with the second AND gate. And here, since the third gate is not required, so all the interconnections of that gate will be kept as it is. That means now, this function f3 is equal to f1 plus AB. So in this way, by providing the feedback from the output to the input side in this PL system, it is possible to implement a Boolean function which requires more product terms. And in this way, we can implement any logic circuit using the PL. So typically, this programming array logic is the one-time programmable. That means once the logic is implemented, then it cannot be changed. But the erasable and the reprogrammable PAL ICs are also available. And popularly, they are known as the GL, where this GL stands for the generic array logic. So this GL ICs can be reprogrammed multiple times. So during our discussion in general, we will refer both of them as the PL. But just remember that the one which is reprogrammable is known as the GL. Alright, so far we have seen that this PL or this programmable array logic has a programmable AND gate array and the fixed OR gate array. But if you see the commercially available PL ICs, then they also have the output logic block that is connected with the OR gate. And the output of this logic block drives the output pin. So here, this I1, I2, I3, etc. are the input pins, while this O1, O2, O3 represents the output pins. So many times, this output logic block is also known as the output macrocell. So in the commercially available PL ICs, this output macrocell can provide the different functionalities at the output side. For example, using this macrocell, it is possible to generate the output function both in the true form as well as the complemented form. So for that, the output of the OR gate is connected with the XOR gate. And one of the input to the XOR gate is the programmable. So let's say the output of this OR gate is equal to F. So whenever the one of the input to the XOR gate is equal to 0, then the output of this XOR gate or this F1 will be equal to F. And whenever this input is equal to 1, then this F1 will be equal to F dash. So in this way, using the XOR gate, it is possible to generate the output both in the true form as well as the complemented form. So this XOR gate is typically part of this output macrocell. And of course, these are the inputs for the AND gate array. So apart from having the functionality of inverting the output using the XOR gate, this macrocell also consists of the tri-state buffer or the inverter. So here let's assume that at the output side we have this tri-state inverter. That means whenever the control input of this tri-state inverter is 1, then it will complement the input. And whenever this control input is 0, then it will act as a open circuit. For example, let's say the output of this OR gate is equal to F. And here let's also assume that this XOR input is equal to 0. That means if we see the output of the XOR gate, then that is equal to F. Now in this condition, if the control input is equal to 1, then the overall output will be equal to F dash. So basically, whenever the control input is equal to 1, then this tri-state inverter will invert the XOR gate output one more time. But whenever this control input is 0, then this tri-state inverter will act as a open circuit. And in this condition, it will isolate the OR gate output from the output pin. So in some PAL ICs, whenever this tri-state buffer or this tri-state inverter is in the high impedance state, at that time, this output pin can also be used as a input pin. That means at the same output pin, we can also apply the input. And through this feedback path and through the buffer, the input and its complement will be available as an additional input to the AND gate array. So in the PL ICs, such pins which provides this functionality is known as the IO pin. That means using the tri-state buffer or the tri-state inverter, it is possible to isolate the output pin, or it can also be used as an input pin. So in some PAL ICs, to enable or disable this tri-state buffer, we may have the dedicated input. While in the some PAL ICs, this tri-state buffer can be enabled or disabled using the additional product term. That means in that case, using the specific input condition, it is possible to enable or disable this tri-state buffer. So far, all the programmable logic devices that we have covered were the combinational one. And using that, we can only implement the combinational circuit. Meaning that those devices did not have any memory element. But in the real world applications, we also need the sequential circuits. So typically in the PAL ICs, some of the outputs are the registered outputs. Meaning that the output of the OR gate or this XOR gate is connected with the flip-flop. And at the rising or the falling clock edge, this output of the OR gate will be stored in the flip-flop. And now, through the tri-state buffer, this output of this flip-flop will be available at the output side. So that is why these outputs are known as the registered output, because they are the output of these flip-flops. So in this registered output, it is also possible to use the present state of the flip-flop as an input. Now if you see the some PAL ICs like 22V10, then the output macrocell is the fully configurable. That means in this IC, through some control pins, it is possible to configure the output as either combinational or the registered output. Moreover, through the programming, it is also possible to use the output pin as an input. And apart from that, it also provides the additional functionality of inverting the output. So we can say that the output macrocell is the fully configurable. And this is the typical logic circuit of the output macrocell of this IC 22V10. So as you can see over here, through these two control pins C1 and C0, this 4x1 multiplexer can be used in the 4 different modes. So whenever this S1 S0 is equal to 0 0, then the output will be the registered output. So in this condition, the multiplexer will select the Q output for the output pin. Now in this condition, if this tri-state buffer is on, then the output will get inverted and the Q bar will available at the output pin. And for this 2 to 1 multiplexer, since the S1 input is equal to 0, so this Q bar output of the flip-flop will be feedback to the input side. So we can say that the present state of the flip-flop will be available as an additional input for this AND gate array. Similarly, when this S1 S0 is equal to 0 1, then the Q bar output of the flip-flop will be selected, and if this tri-state buffer is on, then the Q output will be available at the output pin. And once again, since the S1 is 0, so the flip-flop output will be feedback to the input side. Likewise, when the S1 S0 is equal to 1 0, then the multiplexer will select the OR gate output, and at the output pin, the inverted output will be available. And as you can see, the same output will be feedback to the input side. So likewise, When the S1 S0 is equal to 1 1, then the F output will be available at the output side. And whenever this tri-state buffer is disabled, then even we can apply the input at the external pin. That means whenever the S1 is equal to 0, then the output will provide the registered output, and whenever the S1 is equal to 1, then this output block will act as a combinational IO block. So in this way, the output logic block or the output macro cell of the PL provides the additional functionality on the output side. So that is all regarding the programmable array logic. So in the last couple of videos, we covered the PROM, PLA as well as the PAL. And if you see all these three programmable logic devices, then they are known as the SPLD. That is the simple programmable logic devices. And using these SPLDs, it is possible to implement the various logic designs. But suppose, if you want to implement even larger and much complex designs, then we need to combine multiple such SPLDs. So instead of using the multiple SPLDs separately, what manufacturer used to do? They combine the several SPLDs in the single IC package. So such programmable logic devices are known as the CPLD. That is the complex programmable logic device. So in the upcoming videos, we will learn about the architecture of this CPLD. But I hope in this video, you understood the basic architecture of the PL. So if you have any question or suggestion, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe the channel for more such videos.